everyone. I will speak about a joint paper I wrote last year with David Lee, who's unfortunately not here. And one often finds oneself in a situation where the answer to the problem you're interested in is encoded in homotopy groups of a spectrum. For example, the sphere spectrum, in which case one often approaches the calculation of it. This is a little bit of the motivation for my talk for the classical Adams spectral sequence, where the E2 page of the classical Adams spectral sequence is given by the cohomology of the steam-rod algebra with coefficients in mod p cohomology of your spectrum. And perhaps the most well-studied spectral sequence in history of spectral sequences is in fact the Adams spectral sequence for the sphere itself. The next is the sphere. Might have seen parts of this picture before. I'm going to draw it here at prime 2. If I wrote here the cohomological degree and here the T minus homotopical degree, there's an infinite tower here. This is a spectral sequence of rings spanned by a class H0. Then in degree 1 there's a class H1. These are the so-called Hopf classes H2 and so on. Did I get this right? Maybe this should... No, this is okay. And this infinite family here, the Hopf invariant, these are the Hopf classes, actually extends infinitely. There we have a class H3, H4, and in general we have a class Hi in X1, 2i, where H0 corresponds to multiplication by 2, H1 is the eta map, and H2 is the mu. These are all the Hopf invariant 1 maps, and it's a famous theorem of Adams that actually only the first 4 of those, they all exist on the E2 page of the Adams spectral sequence, only 4 of those exist in the stable homotopy groups of spheres. But you might want to ask yourself, why is there even so much here? Already on the first line we have an infinite family of classes, and every time we have so much space for things to go wrong, they usually do go wrong. And that's exactly what happens here. And the reason is that the cohomology of the sphere is in fact quite simple. It's the base field itself. But you're interested in the base field as a module over the steam-rod algebra. So this is generated by a single element, but there's unfortunately infinitely many relations you need to put on this free rank 1 module to force it to become cohomology of the base field. You have to kill SQ1, SQ2, SQ4, and in general you have to kill all of the even powers of 2, the powers of 2 squares. And it's those relations that actually give rise to those classes Hi. So here you already see the main, perhaps, culprit of the ability of things to go so wrong, namely the steam-rod algebra is not Noetherian. This is a finitely generated module, which is not finitely presented, and those infinitely many relations create lots of space for things to go wrong. In fact, the problem of whether the squares of those classes, which of those survive the spectral sequence, has only been resolved this year. This is a very complicated thing, and this is a little bit of a motivation because I wanted to talk about the other end of the spectrum. What if things are not so complicated? So let's study the spectral sequence for spectra for which such things as an infinite family classes in X1 cannot quite happen. So here's the definition. Due to Maholet and the rest.
Sorry, what did you say about what was resolved this year?
Which of the Hi squares survive the spectral sequence? Oh. That's the covariant variant 1, and that was only resolved this year with the last one. Here's the definition. X is going to be a spectrum, and it is going to be p-complete bounded below. This is enough to guarantee the convergence of the spectral sequence. We're going to say it's Fp, X is Fp, if its cohomology is finitely presented. Over the steam-rod algebra. So a non-example would be the sphere. In fact, no finite spectrum is ever Fp. That's something one can show. But what are the kind of spectra which do happen to be Fp? Where the Eilenberg-MacLane spectrum, for one thing. The Eilenberg-MacLane spectrum, this is going to be my X. the cohomology of the Allenberg-MacLane spectrum is given by the CNOT algebra itself. So that's a free module of rank 1. Similarly, the integers, the p-adic integers, their cohomology is given by a free module quotient by SQ1. Then we have those spectra which are going to play a bigger role later in my talk and which are already mentioned by John Rognes, the truncated Brown-Peterson spectra, where you have to start with a free module of rank 1, and you have to kill those classes Q0, Q1, all the way to Qn, and maybe I should write the upper grading here. But there's a certain family of classes that you have to kill, finitely many, and you obtain the cohomology of BPN. Another example is the real K theory that's given by A star modulo square 1 and square 2. And there's also TMF, where you have to kill square 1, square 2, and square 4. So these are all examples of spectra of FP type, and they're very much infinite. On the other hand, from the point of view of the Adams spectral sequence, they have much better finiteness properties than finite spectra do. So they're very infinite in terms of their homology, but they're very much finitary if you consider them, their cohomology as a module over the CNOT algebra. So, because the cohomology plays a role in determining homotopy through the use of the spectral sequence, you would expect that these kind of spectra have very, very well behaved homotopy groups. And that actually is also true. This is the proposition due to Mahowald and Rusk from the original paper, is that X is the following are equivalent for a p-complete bounded below spectrum. X is Fp, or a second condition, now in terms of homotopy groups, there exists a finite non-zero F, such that if you tensor the homotopy groups of X, if you look at the homotopy groups of F tensor with X, that these homotopy groups are finite. And by finite here I mean finite in each degree. This will be important later. 0 almost everywhere. So another way to think of FP spectra, and this makes it clear that they form a 6 subcategory, something which is not a priori clear using the cohomological definition. They're not necessarily finite, they're not in terms of homotopy groups, but they're finite if you mod out by something. You should think that tensoring with a finite spectrum is modding out by a sequence of elements, and that's because every finite spectrum up to 6 subcategories is given by a quotient of the sphere by some regular sequence p, v1, v2, some powers of those elements. And using this, you can make a sharper definition of what it means to be FP, where we're going to assign to FP spectra a type. So let me make a definition. X is FP type M, type at most M, if this is finite for F finite type n plus 1. There's two remarks here. There's a big jump which seems weird here at first, but you're going to see in examples it's natural. It's type at most n if it's finite after you tensor a finite complex of type n plus 1. And the other thing to be careful with, these form a thick subcategory, but the inclusions go in the other direction than you might be used to if you think of finite spectra. There's a subcategory of FP spectra of type at most -1, and this sits inside the subcategory of finite spectra of type at most 0, silent P, and so on. So this is a sequence of thick subcategories whose union is the thick subcategory of all FP spectra. And each one has the property that all of its objects have finite homotopy with coefficients in a finite complex of type n plus 1. Again, the indexing might seem off the first time you see it, but it does really align with what people mean when they say something like KO is of type 1. Let's see how the types work out here. Well, FP is actually already has finite homotopy groups. It's an FP vector space of dimension 1. So this has finite homotopy. And that means that this is of FP type -1. Now the integers are not themselves finite, but they are finite after you mod out by P. So finite after modding out by P. And that means that the integers are of FP type 0. That's an FP spectrum of FP type 0. BPN has not finite homotopy, it's a polynomial ring and over the integers in classes V1, Vn. So it has finite homotopy after modding out by P, V1, all the way to Vn. So this is an example of FP type spectrum of FP type n. In particular, there exists FP spectra of arbitrary type. This is of FP type 1, KO, and TMF is of FP type 2. In other words, you should think of FP type. It's a good notion of a chromatic height, which only does not make any assumptions on being convex orientable or even having a ring structure. It's some way to measure a height of an object when you're given a spectrum itself. So, Maholt and Resk wrote a paper, I think in '99, where they introduced this class of spectra, and they show it has many remarkable properties. One which I want to mention, which is quite chromatic in nature. Here's a theorem to Maholt and Resk. And this will become quite a bit later today, is that X is of FP type n. Then the map from X into its chromatic localization, this is the finitary localization that appeared in John Rogness's talk. Not so important for us today. This is the localization up to height n. This map is an isomorphism on homotopy groups in large degrees. In other words, spectra of FP type are in a certain sense almost periodic. They are connective, or at least bounded below. They're bounded below. So they cannot themselves be, say, Kn local or Ln local. That would force them to be periodic. But they are essentially up to finitely many homotopy groups, connective covers of their chromatic localizations. So another intuition for what FP spectra are, they're the connective analog, or the bounded below analog of chromatically periodic spectra. You should think they're almost periodic. They're periodic up to some finite amount of noise. Another thing they show, which I'm only going to mention here, one thing you can do, and that's actually quite remarkable, you can take a fiber of this map, take its Brown-Common dual, and what Maholt and Resk show is you get another spectrum of FP type. So there's a notion of duality of FP types. They show that this defines a contravariant autoequivalence on the category of spectra of FP type n. So there's also some notion of duality, which I think we should call Maholt-Resk duality, which again feels like another kind of piece of evidence that you should think that these things are quite finitary, despite being very much infinite as a spectra, very much non-compact. There is a good notion of duality in this context.
Sorry, can you just say again what the construction of the duality is?
So the dual here, there's a notion of a dual of X, which is you would take the fiber of this map, and then you take the Brown-Common dual. And they show that if you do this construction twice, then you end up with the original spectrum. And also, a level of cohomology. The cohomology of this spectrum is in a certain sense dual, in a sense they define to the cohomology of X. So this is some very interesting self-duality of this category. So there it was, the paper written in '99, later discovered, not so much later actually. So John Rogness talked last time about these chromatic redshift and higher arithmetic duality statements. And I think his paper came out in the year 2000 and already used the notion of spectra of FP type So one thing that appeared in John Rognus' talk to say the Quillen-Lichtenbaum conjectures for certain ordinary rings is to say that their algebraic K-theory is of FP type 1. And John conjectured that perhaps the analog of Quillen-Lichtenbaum conjectures for higher rings, these are now proven, is that the algebraic K-theory of a sufficiently nice ring, something like a higher local field from his talk last time, is itself of FP type n+1. And let me mention again the theorem which actually proved this only 3 years ago. This is the celebrated Hahn-Wilson theorem. This is the chromatic redshift. What they show is that if you start with perhaps the most simple ring spectrum of FP type n, namely BPn, and you take its algebraic K-theory, which you have to P-complete, so it becomes a P-complete bounded below object. This is actually of FP type n+1. And one reason this was is really a remarkable result. This shows two things at once. One is the chromatic redshift part, where you see that an object which was originally of height n becomes height n+1 in a very precise sense after applying algebraic K-theory. But this also is, because of this property, some analog of this celebrated Quillen-Lichtenbaum conjectures for higher rings. So this tells you that this map from the algebraic K-theory of K and BPn always P-complete into its Ln+1 localization is actually an isomorphism in large enough degrees. And one way to interpret this result, for example, if we replace BPn by the BP0, which is the ordinary integers, the algebraic K-theory has a canonical filtration which encodes more or less what is known as the motivic cohomology of this ring here. So you should think whatever this ring here is, and this appeared in John's talk, it's closely connected to motivic cohomology of BPn. Now again, if this was an ordinary ring, and we apply the first localization, it's a result of Thomason, but this is essentially the same as a tau G-fication. So what we see here is a tau cohomology. Or more precisely, in this context of higher rings, whatever this is, we should think of this, that this is the analog of a tau cohomology for higher rings. And this result of Hahn-Wilson tells you then, when they show that this is of FP type n+1, is that in large enough degrees, motivic cohomology already satisfies a tau descent. So it's not only chromatic redshift, but it's a very strong qualitative form of the Quillen-Lichtenbaum conjectures as well. But this is a little bit for motivation. When I got interested in this topic, it was actually due to talking to Dylan Wilson and Jeremy Hahn about this. And one thing you see when you look at this long list of examples before Hahn-Wilson, they are all essentially obviously FP type. It's not so hard to show that they're FP types, because BPn itself is very easy to be shown to be an FP type. It's a polynomial ring. So if you model by the generators, it becomes finite. And all of those other things here are actually very close to being BPn. Those literally are BPn. This one becomes BP1 after you model it by eta. And TMF, I think you need to smash with a certain 8-cell complex and it becomes BP2. So all of those things are actually, you should think this is a list of minor variations on BPn. So it's obviously an FP type. This one, it's actually a very complicated theorem to prove that this is FP type. You know, how do they prove this? They approximate this through things like TC. They use trace methods. And TC is some equalizer between TC minus and TP. And both of those things are very much not FP types. In fact, they are very infinite if you model by the first n all the way up to Vn. What happens magically, it's really quite a miracle, is that when you take this equalizer, those both very infinite sides cancel each other out, and the equalizer happens to be FP type. In other words, it's very much not clear if this FP type is a little bit like this. Is it closely related to BPn? So it really begs the question, that's the question they were asking around the time, what kind of FP types are there? So here's a question, can we classify, and to mention another talk from yesterday, I'm asking this question, but I will not answer it. Turns out to be difficult. I will say a bit, but nada matter this. So, can we classify FP types? By which I mean spectra, which are FP. And what I envision here, but again, this is not quite where we are now, is something like the classification of finite spectra up to 6 subcategories. You know that any finite spectrum up to taking 6 subcategories is essentially a quotient of the sphere, and vice versa. And you can always obtain back a quotient of the sphere, a Moore spectrum from any spectrum of type n. So you would want to prove something like this here. But so far, we don't quite even know what would be the generators of the category of FP types. And the conjecture they came up with, and that's the conjecture I will focus on today, Hahn-Wilson, is that FP types, spectra of FP types at most n is exactly the 6th subcategory. Generated by BPM. Any questions so far?
So if you knew this conjecture, does that mean that you would know the Hahn-Wilson result for the FP type n?
No, what it would tell you, and but I think this should be a little bit easier than the general conjecture, is that this belongs to the 6th subcategory of BPM plus 1. And presumably, because this thing is not FP type n, you could also reverse it and show using their calculations that this also generates the same 6 subcategories as BPM plus 1. So you get like a very clean version of redshift. That up to 6 subcategories, the K-theory of BPN literally is BPM plus 1. So that's one thing that this would imply. It's a great question. But let me warn you why this actually is perhaps, why this might potentially be difficult. And why I think this case is not quite as bad, even though we didn't resolve this one yet, but I would be really interested in seeing someone do this. This case is not quite as bad as this, the general case. So one corollary of this, I want to say corollary because it hasn't yet been proven. This would imply that if X is FP type, and most n, then it satisfies the telescope conjecture. Then the Tn localization of X is the same as Kn localization of X. Which, of course, is actually 2 years ago here in the UK in Oxford, the conference right before the Newton Institute one, the negative solution to the telescope conjecture was announced to Birkeland, Levi, Schlank, and Hahn. So this is not true in general. There are spectra which fail this, but worse yet, what we mentioned is here, the counterexamples to the telescope conjecture they produce are not FP type, because then we would know that this is false, but they're somewhat close. So there exists X, what they show, such that it fails the telescope conjecture. And if you look at its homotopy groups with coefficients in a finite spectrum, then this is not quite finite, but it's bounded. It's only non-zero in finitely many degrees. So there exist counterexamples to the telescope conjecture which are quite close to being FP type. In particular, they also have this property. So if this conjecture is true, if the Hahn-Wilson conjecture is true, it also gives you some measurement of how badly the telescope conjecture can fail. You see that we know it can fail here, but it's asking what if it's actually finite? So you have a relatively reasonable object. Can it still fail then? And I should mention this actually, this conjecture, this thing here appears in the original paper of Mahoel and Rest. This is the Mahoel-Rest conjecture. I think at the time when they wrote it in '99, they already believed that the telescope conjecture is probably false in general, but they still thought it might be plausible that it's true for reasonable things, like FP types. And one way to prove something like this would be to prove the Hahn-Wilson conjecture itself. So, I should probably tell you a bit how I became interested in this. So Dylan was in grad school with me at Northwestern, and then I became a postdoc at Harvard, and Dylan was also a postdoc at Harvard at the time. And in 2022, I think it was when they first had a whiff of this, it was maybe late 2021, they proved this, and they started asking around in Cambridge, Massachusetts in this case, about, oh, like, is this thing actually BPM plus 1? What can we prove about FP types? But like, I didn't quite know the details, and Dylan told me that if I want to know the details, I actually have to go to MIT to talk to Jeremy. Which I did. And because I wanted to get into something new, I was looking for a new problem to work on. So I went to Jeremy and asked him if he has some new problems. I heard those whispered, they're thinking about FP types now, that it's the whole new thing. And Jeremy was sitting in his office, petting his cat, and he says, I've known you for many years, and yet this is the first time you come to me for counsel or for help. I can't remember the last time you invited me over to your house for a cup of coffee. Let's be frank, you don't want my friendship. I can't act like I didn't want to get in trouble with Mike. I understand. You found paradise in America. You didn't need men like me. You need men like me. But now you come here to me and you say, don't Jeremy, give me a problem. But you don't come with respect. You don't offer friendship. You don't even think of calling me God Jeremy. And I say, how much shall I pay you, Jeremy? Piotr, what did I ever do for you to disrespect me so much? If you had come to me with friendship, you would be working on a new problem this very day. And I said, I bowed my head and I kissed his ring. And I said, be my friend, don't Jeremy. And that's how I ended up working on this problem. Better yet, Jeremy offered, after I pleaded my fealty, to offer me the help of one of his best, of his new grad students at the time, David Lee, and we started working on this problem together around 3 years ago. Very, very happy with how this turned out. Okay, so why am I happy with how this turned out? Again, like I told you, it's quite difficult. And it's largely difficult because of this part. We spent a lot of time trying to work on proving something more like this, and it turned out to be quite difficult. So eventually we tried to focus on the part of the story where we kind of assume that the telescope conjecture is true, and then see what we can prove then. So one place where the telescope conjecture is true is at height 1. And in a joint paper with from last year with David, we're able to prove that the Hahn-Wilson conjecture is true at height 1. Is true at height 1. In other words, spectra of FP type n plus 1, at most FP type at most 1, which again, these are spectra which are finite modulo P modulo V1. A finite homotopy modulo P V1 is exactly the fixed subcategory generated by VP1, which is also more concretely the fixed subcategory of complex K theory. And I should say that Mahout and rest never quite make this conjecture in their paper, but they do, for example, mention, they write, I think in one of the footnotes, that C-1, this is the category of spectra of finite homotopy groups, is the fixed subcategory generated by FP, and C0 is the fixed subcategory generated by the integers. And C1 contains the fixed subcategory generated by KU. So they don't quite make the statement, but you can see how this theorem completes like a very natural pattern. this is the subcategory generated by FP, the integers, and finally C1 is exactly the fixed subcategory generated by complex K theory. So how do we prove this? Well, like I mentioned, we're using that the telescope conjecture is true at height 1. But what we actually prove is a statement that's true at all heights, but we do it by moving away from the possible truth of failure of the telescope conjecture, by which we mean we work entirely in the K local world. And there we're able to prove a theorem that's true at all heights, and that's what I wanted to tell you next. So let me tell you a little bit of the monochromatic story. So this is the monochromatic Hahn-Wilson. So we wanted first to define what is a natural analog of spectra of FP type in the K and local category. So this is all going to be in the K and local category. So here's the definition. Let me say that X is a K and local spectrum now. We're going to say that it's locally FP, or maybe it's more clear, K and locally FP, if its homotopy groups are finite. You cannot use the cohomological characterization here, at least a priori, because the Albert-MacLane spectrum is 0 in the K and local category. So we're going to use the definition using homotopy groups. We're going to say that this is finite. And now, the thing is, K local spectra are always periodic after you mod out by all the way up to Vn minus 1. So there is no way this can literally be finite, as in finite and 0 all but everywhere. But you can ask it to be finite in all but in each degree. So that's what we found. If this is finite in each degree, where V is a finite complex of type n. There's two differences here to the definition in the bounded below case. For one thing, I'm asking it to be finite in each degree and not to be finite in each degree and 0 almost everywhere. And you also have to be, and this is what actually corresponds to this jump here. We're asking V to be a finite complex of type n. Here it was really a finite complex of type n plus 1, but this is actually how things match up. So let me give you an example. If X is FP type n, at most n, and it satisfies the telescope, then its K localization is locally FP. In other words, this really is the analog of being of FP type n, despite being some grading changes. You should think being of FP type at most n, it means that you're finite after you mod out by Vn. But what this means that if instead of modding out by Vn you invert it, you get a finite dimensional vector space. And that gives you this finite, being finite in each degree. So in particular, the K localization of VPN is an example. Or in fact, any FP type spectrum which satisfies the Mahorald-Ress conjecture. So it satisfies the telescope, provides you an example of a monochromatic spectrum of FP type. But there's new examples now here. So like I mentioned, in the bounded below case, no finite spectrum can ever be FP. As it turns out, in the monochromatic story, finite spectra always are FP. So the K localization of, let's call this maybe P, for any finite P. So this is something that you already see how the monochromatic story becomes quite a bit different in its behavior from the integral story or the bounded below story, where because of the very good finiteness properties of the monochromatic category, finite spectra are actually examples of FP types, of local FP types.
Sorry, Piotr,
yeah.
For this statement, maybe you said it in words. You want to say LKN of X is locally FP type less than or equal to n?
I guess I only defined it without, but I should say like locally fp at most n, yeah, and this would be locally fp at most n. So you could a priori define variants of this definition, but we really only define locally of type at most n, which in this case is also exactly n, because it cannot be more than this in the Kn local category. That's a great question. So I will only really speak of Kn local spectra which are locally fpn, by which I mean
Your
this
ends
definition.
now are completely different, right?
Here, they're the same everywhere.
I mean, the type of the complex and the chromatic height in your mouth Kn.
No, so I will only, that's what I want to say. And in this talk, I will only consider when they're the same. Yeah. But I think you could potentially consider variants of this in general when they're different. But I will only do at the height. And the theorem we're able to prove with David at any height in the monochromatic story is the natural analog of the Hahn-Wilson conjecture, namely locally P spectra is the same as the fixed subcategory generated by the Kn localization of EPN. And using the fact that the telescope conjecture is true at height 1 and some other properties that I don't want to get into that are probably not so essential, we're able to deduce the integral statement from this statement at height 1 at larger heights. It is quite difficult because, again, you need to deal with the telescope conjecture first. I wanted to give you a little bit of a glimpse what kind of things that go into the proof of this theorem, but also why does it really become so much easier once you start working Kn locally? It really suddenly feels like you have so many more tools. And I will do some erasing, so this would be a good moment for any questions.
So if you just define this like type less than or equal to k less than m.
Sorry?
If you did make a definition where you separate the
Yeah.
ends and the keys. Sorry, you can keep reading.
No, oh yes, you're right. Yeah.
Would you expect that this statement, this example is true still? Lkn of t of x is locally fp. Sorry, Lkn of x. If I put a t as my less than or equal to thing in both places, then Kn localization would still preserve the less than or equal to. Sorry,
No, I understand your question. I actually never thought about this.
Could you repeat the question, please?
Yeah.
So the question is, if in this example over here, you replace n in the instances that there's a less than or equal to immediately before it with t, is the statement still true?
So I know about like the case where k is different than n, but if you start with something which is of type fp type less than n, then it's also of fp type n, so it will still satisfy this theorem. And if it's of fp type larger than n, then it's 0 after Kn localization. So there's definitely, you can consider what happens below n, but as soon as you go above n, there's nothing Kn locally. But I haven't actually thought what happens for smaller n. I think that would be a very interesting question. Okay, how do we approach this problem? Actually, is the Kn local category is well understood. And perhaps one of the reasons it's so well understood is, you see, if you want to go from the sphere to BPN, it's really not quite clear. It's not quite a Galois extension in any reasonable sense. But Kn locally, it almost is. So let me get into some your recollection. I say recollection, but it's really, there will be some things I will need to use, which are quite heavy facts about the Kn local category. If you look at the Kn local sphere, there's this Galois extension, which is in a certain sense a universal cover, and the thing called Morava K theory, Morava E theory. This is Morava E theory. And this is a Galois extension with a very nice Galois group. This Galois group is known as the Morava stabilizer group. and it's actually a p-adic analytic group. So you should think this is the p-adic analog group of a compact Lie group, where instead of using things that locally look like the reals, it locally looks like the p-adic numbers of dimension n squared. So it actually gives it excellent cohomological properties. And the reason this fits so nicely with this conjecture, because actually Morava-E theory, it almost is the Kane localization of BPN. So it's actually a finite module, finite free module. This is a finite sum of Kane localizations of BPN. So this is the connection we're going to exploit, and you should think the way we're going to use this is we have some information about the homotopy groups of our X, perhaps with coefficients in a finite complex. So we have some information how it looks from the point of view of the Kane locus sphere, and we're going to try to deduce some information and show that it actually must be closely related to Morava-E theory. So this Galois extension really fits very nicely into the problem we're going to try to work in. In fact, in these terms, we're able to prove a slightly refinement of this theorem. So it's actually, you can prove a more precise statement if instead of working with BPN, you're working with Morava-E theory. And I think that's of interest of its own right. So I'm going to put it here, because it actually elucidates the proof quite a bit. So the following are equivalent for a Kane locus spectrum. One is that it's FP, or it's locally FP. So again, what this means is that this is finite. Finite in each decay. Two, and that's actually quite interesting because this is the analog of the original criterion due to Mahout and Resk, except in the Kane local category, where this turns out to be equivalent to the cohomology of X being finitely generated over the dual C-node algebra, the C-node algebra of Morava-E theory. So this result actually tells you that from the point of view of the Kane local category, you can also characterize locally FP things in the same way you do in the bounded below case, but now what used to be mostly cohomology becomes Morava-E theory. Three, and this is the interesting part, X is in the fixed category generated by Morava-E theory, which is also the fixed category generated by BPN. So that's actually the theorem I just stated. And finally, this was actually pointed to us by Strickland after we emailed him. We already had those three written out, and he immediately came up with a really cool idea where he observed that Morava-E theory, it's not quite dualizable. So it's not something like a finite spectrum in the Kane local category, but it's weakly dualizable. The canonical map into its double dual is an equivalence. So that's being called reflexive. So X is reflexive, i.e. the canonical map into the double dual is an equivalence. So this is the monoidal double dual. So this is what you... By a monoidal dual of a non-necessarily dualizable thing, I mean the mapping spectrum into the Kane local sphere. So the last characterization here, actually, I think it's particularly interesting because it uses no information about the Kane local category, but its monoidal structure. So again, it shows you that this is a very natural class of spectra that we think was overlooked for quite a bit, because it can be characterized in so many different ways. In fact, arguably more ways than the bounded below case, because this new characterization, which was pointed to us by Strickland, is very much a Kane local thing, I think. So, and I wanted to draw you a picture, actually. I'm going to again mention Strickland. There's a huge monograph, huge maybe not in terms of how long it is, but how useful it is. It's a wonderful book by Hovey Strickland on the Kane local category. And this is this kind of The fact that such a book already exists is exactly that gives you the methods to prove theorems like that. And they observe, they study different classes of K-local spectra in this book. So here, maybe here's the K-local world. And the smallest one, a natural class of K-local spectra to consider is the compact objects. So these are all actually retracts of a K localization of a finite complex of type n, and they can be characterized by the property that their ecohomology is finite. Finite in each degree. Now there's a slightly larger class here of dualizable objects. So here is where you would have the K localization of any finite spectrum, not necessarily of type n. And they also show in Hovey-Strickland that they are characterized by the cohomology being finitely generated, but not over the Stenon algebra. It's finally generated over the base ring, over E star. Now we're showing in our theorem that there's yet one more natural class of objects to put in here. And all of these inclusions are strict. The sphere is here, but it's not here. And here I have locally Fp, which is also the same as reflexive, which is also the same as the cohomology being finitely generated over E star E, over the Stenon algebra. So there's really quite like an onion. The K-local category is an onion of objects with better and better finiteness properties. And what I really think quite amazing is that this Galois extension, this Moravai theory thing, really controls in such a natural way where you fit in. Like there are different ways to measure what it means for an E star module to be finite. It can be finite in each degree, finally generated over the base ring, or finally generated when you also allow the cohomology operations. And they all define very natural class of objects. And again, this is not how the story looks in the bounded below context. In the bounded below context, finite things are not themselves Fp. In fact, never. Okay. I will tell you, not too much, but perhaps how you would go about proving such things. Like I mentioned, large parts were already in the literature, a lot of tools that we were able to use already in the literature. So some of those implications are easier than others. And I'm going to give you some keywords to convince you how you might want to go about proving something like this. So 1 to 2, well, that's actually the hard part. So I'm going to talk about this in the very end. But the other one are not so bad. So one thing, I gave this talk twice before, and science people ask. Notice there I used the notion finitely generated instead of finitely presented. And the reason I got away with this, and one of the main reasons the K-local category behaves so much better than the bounded below one, is because this ring is already in a theorem. In fact, this ring here is a group algebra over E star of this Morava stabilizer group. And this group itself is not quite yet of finite cohomological dimension, but it has an open subgroup of finite cohomological dimension. So inside here you have a subring, which is the group ring of this very nice ring. And this ring, because this is a regular local ring, and this is a group of finite cohomological dimension, is actually a finite global dimension. So that's actually one huge difference you already see with why the K-local story is so much easy. The dual Stenon algebra is very much not of finite cohomological dimension and is not Noetherian. The analog in the K-local story is not quite itself of finite global dimension, but it's a finite module over a subring. It's a finite module, finite rank, over a ring of finite global dimension. So how you would prove that to imply 3? Well, you know that its cohomology is finally generated, And if you consider the cohomology as a module over this ring is of finite global dimension, so now there's actually a finite projective resolution. The finite generate module of a ring of finite global dimension is a finite projective resolution, and you can try to lift this resolution to build an Adams resolution where you're going to build X out of pieces that look like E. The one thing that you have to be careful with here is you're really working over this ring, but you really want to be here. So there's a final step that we use, which is essentially some form of Galois descent along the map from the K locosphere, which is the same as the fixed points of the Morava E theory with respect to Gn, and here we take the fixed points with respect to U. And this uses a very nice paper, actually, of Bartel, Hurd, and Neumann. So using their work, one can show, they show actually that this ring, that the K locosphere is in the fixed tensor ideal generated by this finite extension, and that's exactly the step that allows you to go back. You know by some arguments involving this, something happens if you base change your scalars to here, and using this result, we go back to the K locosphere. So these are the 2 and 3, and there's I will say even less about the other 2 implications, because we actually have to do even a bit less. These were largely quite simple arguments using what was already known. So 3 and 4 is you want to show that if something belongs to a fixed subcategory of E, then it's reflexive. But E itself is reflexive by a result of Strickland, which is precisely why when we emailed Neil Strickland, he asked us about this. So 3 implies 4 is Strickland. The theorem of Strickland. And finally, 4 implies 1. So you know that something is reflexive, and you want to show that it's finite homotopy groups with coefficients in a finite complex of type n. That's essentially follows from what's known as Gross-Hopkins duality. So Gross-Hopkins duality is a statement that relates the Spanier-Whitehead duality in the K local category with the Brown-Comenetz duality. They differ essentially by an invertible object. So here we have something that's monoidal double dual of itself, and by Gross-Hopkins duality, it's also a Brown-Comenetz double dual of itself. And from there, you can verify that it must have finite homotopy groups, because the only finite abelian groups which are Pontryagin self-dual are finite. Okay, last 5 minutes, the hard part. So this is where you actually have to prove, and the hard part, notice, is essentially that the part of the Hahn-Wilson conjecture. You know something about homotopy, and you want to deduce something about cohomology, which then almost immediately implies that you live in the fixed subcategory generated by Morava E theory. So one thing you might want to try, there's an analog of the Adams spectral sequence in the K local context, where you start with the knowledge of this, and you calculate homotopy groups. So that's what we tried first. But this turns out to be really quite complicated. By a miracle, it actually works at height 1, by like a tricky, by like a sleight of hand, essentially. But the hard part is, you know, you're trying to reverse a spectral sequence. You know that it's finite on the infinity page, and you try to deduce that the E2 page has some good finiteness properties. And that's a recipe for a disaster, because you're trying to go backwards, and lots of cancellations might have happened. And in fact, as far as we know homotopy theory, whenever there is room for cancellations, they do tend to happen. So we didn't quite use the Adams-Novikov spectral sequence. And we came up with the idea of working directly with this information we have. So the idea was to choose a nice V, which is of type n, finite type n. By nice, I mean, for example, it's a ring spectrum. And then you started to run the universal coefficient spectral sequence. Where, how would it look? You would start with the V homology of X and go into the V homology of E, all going over V star, and this would calculate the E tensor V cohomology of X. So you rarely see a spectral sequence like this, especially in the bounded below case, because here the input into the spectral sequence is the thing that is usually harder to calculate. You need to know the V homology of X. So it's homotopy groups essentially, and that's hard. But you see, actually in the FP, locally FP case, this thing we understand. It's finite in each degree, so there's very good finiteness properties. The thing that should worry you more about here, we also have here a homotopy groups of a finite complex. K local. K local, but still, calculating homotopy groups of finite complexes, it's usually a tall order, even K locally. The last theorem I wanted to state to you, what we use here is we actually prove that K locally, there do exist finite complexes with very nice homotopy groups. Maybe I will leave this here, which we're quite surprised in. Once we know that there is a finite complex with particularly nice homotopy groups, we're able to analyze this spectral sequence. It turns out to have a collapse at the finite page, and the E infinity page is finitely generated, and then we're able to deduce that the cohomology itself is finitely generated using some completeness arguments. So here's the construction. And the construction already uses actually a recent breakthrough result of Robert Burklund, that there exist finite ring spectra, and they can actually be made coherent. So what there's up here, Burklund shows that if you start with the sphere, and you mod out by some generators here, to make this type N, by Burklund this is actually a ring spectrum. For large enough indices. By which I mean it can be made En ring spectrum for any n, if you choose your indices large enough. So that's actually quite close to what we need, but we're going to take this V, and then we're going to tensor with this finite Galois extension of the K local sphere. And this has the effect that the Adams-Novikov spectral sequence calculating the homotopy groups of V has cohomology, has E2 page given by cohomology of U in coefficients with E star modulo the ideal I generated by those generators here. And because if U is small enough, this is actually bounded above, as in like it's a finite cohomological dimension group. And the last theorem I wanted to mention here, this is also with David, is that for small enough subgroups U, this is actually a very nice finite complex. For small enough U, so what do I mean by this one? The E2 page of this spectral sequence, so these cohomology groups are actually given by an exterior algebra. This is E star E on n squared generators. 2, so not only and this actually is essentially a very slight strengthening of a result of Lazard. Lazard shows that if you have a very nice periodic analytic group, then its cohomology of FP coefficients is exterior. We show that you can make this happen for cohomology of coefficients in Z mod P to the K, if you make the group small enough. And 2, here's the hard part, is that this spectral sequence collapses on the second page. And finally, we show that this implies that the homotopy groups of this B are also given by an exterior algebra on some generators x1. And that's actually what you would want here. You might think, well, exterior algebra is not such a nice ring, but actually in this case that's exactly what you want, because you're not so much interested in this ring, but in the cohomology of this ring, so those X groups. And the cohomology of exterior algebra is polynomial. So in this case, it's actually going to be a polynomial ring concentrated in even degrees. So you actually end up with like a spectral sequence, which is a module of a different spectral sequence with extremely well-behaved finiteness properties. And that's how we're able to analyze this universal coefficient spectral sequence here. Thanks so much for listening.
Questions? So in the redshift theorem, that like K-theory of BPN is finite.
Yeah.
Is it very like the finitely presented part? Is it very specific to BPN or if you had some?
The fact that it's FP or?
Yeah.
So it's, well, I'm not too familiar with the proof, but I think it's things like BPN. So yesterday, John Rogness talked about, there was this notion of higher local fields. And actually one of the assumptions was that there were like, BPN was one example. But I think the conclusion of their theorem was that for all of those higher local fields, did I get this right? Their K-theory is in fact FP of higher height. So it cannot be arbitrary, presumably. There's some regularity you need to assume. But it's more than just BPN.
Questions?
Yeah, one of the basic facts about K-local homotopy theory is that the E-based atom spectral sequence has a horizontal finch. But the proof of that, to find that in the literature, is a little bit complicated.
Can you get a clean proof of that using these techniques?
I haven't thought about this, but like there is one in your paper with Anis and
But we're just copying over from from some more elusive source.
I haven't thought about this, but one thing I would hope that maybe there's some things that we already know or that we couldn't know that could be reproven again or proven for the first time using those finite complexes. I would hope that this is like something that you could use to prove other things. Because this technology, especially this resemble Berkeley, just did not exist a few years ago. So I really hope that there's some other things you could use it for, but I haven't thought about it too much.
Is the fact that finite spectra are locally FP in the K and local have any major consequences?
Some consequences of?
Yeah, like in these theorems, like as opposed to the orbital.
So it's actually, this essentially follows from this thing here.
So the question was, does the fact that finite spectra are locally FP in the K and local world have any major consequences in terms of difference to the bounded below world in these theorems?
So, this is what you mean. So I don't think so much for these theorems. They define examples, and it doesn't really affect the proof so much. But it's definitely, maybe I would say, the fact that this is true is closely related to the way you prove this. The way Hobby-Strickland proved this is using arguments that are very similar. So I wouldn't say it doesn't necessarily imply this, but it's implied by a lot of the same things. So it's closely related in this way.
There is a sense in which the connective covers of the element localizations are bound with finite spectra are expected to be.
Right, so maybe I should mention that there's some other examples of bounded below FP types, which Mahowat and Rez give, which are related to this fact, actually, what Jeremy just mentioned. For example, if you start with X a finite spectrum, and you take its L1 localization, and then you take the connective cover, then this is FP type at most 1. And it's also true at height 2, at primes, I think, above 5, and one could expect that maybe it's always true. So maybe what Jeremy is saying that, like, at least conjecturally and in a lot of examples, connective covers of localizations of finite spectra are themselves FP type. So again, you see there's this connection between to go from something that's finite to something that's FP, it often involves some kind of chromatic localization. And then if you work in a chromatically localized world, then it's actually an inclusion.
Okay, let's thank Piotr again.